Okay, so let us for the last time in this course look at planning. And so, as I said, in the mid 90s there was a series of approaches to planning which produced much longer plans, which means they were much faster algorithms and could sort of solve larger problems. All these approaches were two stage approaches. It means that you have a planning problem, you convert it into something else and solve that problem essentially. So, one thing that was very successful was that if you convert it into a SAT problem, and we are already familiar with SAT, and then you could use some solver. In fact, there was a algorithm called SAT plan which was very successful in the mid 90s and early part of this century. So, how do we know it was a good algorithm? There is every 2 years a competition called IPC, International Planning Competition, in which people submit their programs. So, just like you had this traveling salesman problem competition, in this you submit your planner and they try it out on a set of problems, and then the planner which works best is judged to be the winner. So, SAT plan was one of those planners which did very well for a period of time, and what it did was to convert a planning problem into a satisfiability problem and then solved it using its own algorithm, of course, but you could use off the shelf solvers for satisfiability. Another approach was to convert a planning problem into a CSP problem, which as the name suggests converts this into a CSP, and by CSP we mean a constraint satisfaction problem. We will look at them briefly in the next 2 lectures and then solve the CSP. So, you are posing it as a different problem and then using some solvers to solve it. This is a recurring theme in many problem solving situations. What GraphPlan does is to convert it into a structure called a planning graph. And this is the algorithm we want to look at today, and it is called GraphPlan. It was given in 1995 by 2 researchers called Blum, who is now at CMU I think, and First. So, fairly recent by in contrast to the other algorithms that we have seen, all those algorithms are quite old in some sense. So, as a name, as I said, what this does is it constructs a structure called a planning graph and then searches in the structure for a plan. All these 3 algorithms have one thing in common, is that the conversion that they do in the case of either SAT or CSP or planning graph is incremental in nature. So, they construct a structure of certain size and then see if there is a plan there, a little bit like DFID you might say, keep exploring longer and longer plans to see when you can find a plan. And because of that, all these algorithms end up finding the optimal solutions as well, because they incrementally search for longer plans essentially. So, you can imagine that whatever the mechanism for converting it into a SAT problem is, it is a relation between actions and states and new states and new actions and so on, and you express this as a satisfiability problem. Things like precondition of this must be satisfied by the action by something, and that kind of stuff, and they always find shortest plans. So, let us start by looking at the planning graph structure. The planning graph is a layered graph with alternate layers of propositions and actions essentially. So, there is a layer P0 which contains all the start propositions. Then there is a layer A1 which is the layer of all possible actions which can be done at the first time instance, followed by a layer P1 which consists of all the propositions which could possibly be true at the end of the first layer essentially. Now, the difference between the other algorithms, heuristic search, we just briefly mentioned in the passing that you could have forward state space search or backward state space search with a heuristic function, which was computed by solving a relaxed planning problem to decide which successor is best. That search, heuristic search or state space search, searches in the set of states. Plan space search that we saw in the last class searches in the space of plans. Here we search in a structure called a planning graph, which is in some sense a union of all possible states that can happen essentially. So, if I have, for example, a start state and I can do action A1 to go to state S1 and I can do action A2 to go to state S2. That is what heuristic search would do, forward state space search would do. It would say, should I go to S1 or should I go to S2? In GraphPlan, what you do is you have this layer, start layer, then you have this first action layer which includes both these actions A1 and A2, and then you have a layer which is basically the union, or let me just write S1 union S2. We put together all the possible predicates into one set, which is in this next layer of the proposition. So, we have this proposition layers and action layers essentially. So, one thing with all these algorithms do is to first convert this problem into a propositional problem, which means that if I have an operator like pick up or put down or so on, you look at what the starting state is, what the objects in the domain are. So, let us say I have 5 blocks A, B, C, D, E, then it will produce all possible actions with these 5 blocks, pick up A, stack A onto B, stack A onto C, all possible actions it produces and works with those actions essentially. So, I want to give you a flavor of this. So, let us just work with this with the same example that we are looking at the suspense anomaly, which means we are starting with this state C is on A and B is on the table and they are on the table essentially. So, in the initial layer, in layer P0, we would have all these things. So, let us say arm empty, then on table B, clear B, on table A, on C A, clear C. These so this is P0, my layer P0. Now, there are 4 kinds of edges in the planning graph. The first is precondition edges, which go from an action to some precondition in the previous layer. Then effects positive edges, effects minus edges, and one more set of edges which is called mutex relation. Now, we are already familiar with the precondition edges, the positive effects and the negative effects. We will look at what mutex is in a moment essentially. So, in the initial layer we have this proportion. So, it is a proportional layer 0 P 0, then we have action layer 1 in which we want to insert all actions which are possible in these propositions, and we want to put a slight additional constraint that the preconditions of those actions must be possibly true at the same time. So, if they are possibly true at the same time, we will consider such an action. That is where this notion of mutex relations will come. So, as you probably know, this is an often used term. So, mutual exclusion essentially. So, we will have this notion of, so this mutex relation is going to be these edges are going to be inside each layer essentially. So, this layer will have its own mutex relations, this layer will have its own mutex relation. They are from one action to another in an action layer, or from one proposition to another in a proposition layer, and if an edge exists between two entities, either two actions or two propositions, it means that they cannot be true at the same time. So, if there is a mutex between A1 and A2, it means they both cannot be done at the same time. As you can see in this example, we have two actions, unstack C from A or pick up B, and we can see that they cannot be done at the same time, because they both require the arm to be empty and only one can use the arm essentially. So, we would have a mutex relation between them. Likewise, there are mutex relations between propositions which say that those things cannot be true at the same time. One thing which happens constantly as we construct the planning, so we construct the planning graph from left to right, we keep inserting actions, then propositions, then actions, then propositions, then actions, and propositions. Till what time do we do that? Till the time when the goal propositions appear in a proposition layer and they are not mutually exclusive. So, what are the goal propositions that we are interested in? In our case, we are interested in on AB and on BC. If these two propositions occur in the proposition layer, in fact, the first time they occur in the proposition layer and they are not mutex, which means they are not mutually exclusive as per the planning graph, then there is a possibility that we have solved the problem. So, that at that point the first stage of the algorithm, which is the forward phase, halts, and the second stage begins, which says that is there actually a plan which will achieve both those goal conditions for me or not essentially. So, it is a two stage problem. You construct a planning graph, search for a solution. If you cannot extend the planning graph by more, search for a solution, and you keep doing that essentially. Now, one action which is a uniform action which we always insert is called a no op, and a no op has any predicate P as an input and the same predicate P as an output essentially. So, as the name suggests, it says there is no operation we are doing on this predicate, and so we will depict no ops by these lines like this initially, but we will not draw them after that. Because they really take up too much space. So, as a effect of this, in P1 we will have the same actions, clear B on table B, arm empty on C A, clear C. This we will do all the time. In every layer we will always insert no op actions, and you can see the effect of this no op actions is going to be that the planning graph is going to grow monotonically. The sets of propositions in the proposition layer is going to grow monotonically, because whatever is present in the previous layer will always be carried forward to the next layer, plus of course new things may be added essentially. So, what are the new things which can be added? In our example, we have the action unstack, no, so let me write this here, pick up B, so that I can add to this. Why can I add to this? Because its preconditions that B is clear, that B is on the table and arm is empty is true. Maybe I should have written this a little bit that side, okay, but we will manage. Then, so this is the first kind of links we have edges we have mentioned, the precondition edges. Then the second kind of edges are positive effects. So, the effect of pickup B is holding B. So, I have a positive edge from this to holding B, and I have negative edges to its negative effects, which is on table B. So, I have a negative edge going from here. So, we will depict a let us say we can depict a negative edge like this, and for argument's sake we will assume that this also becomes false at the end of it and arm empty. So, that is a third kind of edges. So, first kind is precondition edges, which go from a proposition to an action layer, and they basically capture the preconditions that are necessary for those action to be applicable. The second kind is the positive effects, which is what would be true in the next layer of proposition if that action were to be executed. And in that sense, you can see that no op basically says that if that no op action were to be executed, then on table A would continue to be true. Okay, so this should have been here. On table A was true here, and if I do a no op, then on table A will be true in the next layer essentially. So, that is one more action, and one more action we can add is unstack. You see from A, and you can see that the preconditions for that is that R must be empty, that A must be on the table A, and C must be clear. So, all these 4 conditions are preconditions for that. The effect of that is holding C and clear A, and the negative effect is that we have assumed that we will mark this like this, that C is no longer clear, C is no longer on A, and the arm is no longer empty essentially. So, when do we have mutex relations? That is the how do we define that two entities in a layer are mutex essentially. So, let us talk of actions first. There are 4 conditions under which action are mutex. So, we say A1 and A2 are mutex if one of these conditions holds. The first is that P1 belongs to precondition of A1 and P2 belongs to precondition of A2 and mutex P1 P2. So, when I say mutex P1 P2, I mean there is an edge between P1 and P2 which says that they are mutex. So, if A1 requires P1 as a precondition and A2 requires P2 as a precondition, and the previous layer those two are marked as mutex, then those actions cannot be done together essentially. 2 if P belongs to if x plus of A1 and P belongs to effects minus of A2. The second condition for two actions to be mutex is that there is some predicate P which is a positive effect of. So, that is in the next layer, right. Remember that these effect links go from the action layer to the next layer, and we are trying to decide whether any two actions in the action layer are mutex or not. So, if action A1 produces P and if action A2 deletes P, so that means it is the negative effects of A2, then A1 and A2 are mutex. They can never happen at the same time, because the semantics of these two actions happening in parallel is not defined essentially. So, GraphPlan in general will allow us to develop parallel plans, which means if we had a 2-armed robot, for example, then the 2-armed robot could have simultaneously picked up C from A and picked up B from the table and done something with them essentially. So, parallel actions are in general allowed. Of course, we have put both these actions in our action layer, but we know, being now familiar with this one-armed robot and how it can operate, that only one of those actions can happen, which means that these actions must be marked as mutex somehow essentially. So, we will see, this is not the condition for that, but one condition is that if one action is producing something P and the other action is deleting P. So, we do not know if both were to happen together whether P would be true or whether P would be false, and if you were to linearize them, then the final effect of those two sequential actions would change depending on the order essentially. So, we cannot do that. One condition, a third condition is that P belongs to effects minus of A1 and P belongs to precondition of A2. So, if a predicate P is required by action A2 and predicate P is being deleted by action A1, then we say that A1 and A2 cannot be in parallel. Again, the reason for this is that if we were to linearize them, then the two orders will not produce the same effect essentially. For example, if you were to do A1 first, then it would delete P and then you cannot do A2 after that. You could do A2 first and A1 afterwards, but then you can see that the effect of these two actions is different. We want our parallel plans to be such that they can always be linearized to give us a solution plan. So, that is one more condition, and the fourth condition is that, let me just draw it like this. If A1 produces P and deletes P, and if A2 also does that, it consumes P and deletes P. If both of them are consuming something, so this, remember this dot stands for deleting P, it is a negative edge. It is saying that P is a condition for A1 and not P is the effect of A1. This is also saying that P is a condition for A2 and not P is an effect for A2. So, if both the actions, so it is something which you are consuming and there is only one cake and there are two people, so only one of them can eat it essentially. So, both cannot be put into the planning graph as saying A is eating the cake and B is eating the cake. Or in our example, you can see that there is a negative edge from to arm empty from pickup B, that this is going to delete arm empty and this is also going to delete arm empty, both are consuming arm empty. So, this fourth case applies to this and we mark a mutex edge between this and this. You can also see that this no op is mutex with pickup B, because this no op is producing clear B and this pickup B is deleting clear B. So, the second clause which says that one of them is producing it and the other one is deleting it, then these two actions cannot happen in parallel. So, we have to, so as you can imagine there would be many mutex edges between actions that we will have to find. So, one mutex edge that we have is between this and this, another mutex edge is between these two, and there are others of course that you can find essentially. So, that takes care of the action layer. Then mutex relations between propositions P1 and P2 are mutex. So, P1 and P2 are propositions in the same layer obviously, mutex relations are always within a layer. If there is I will just write a long explanation, let me see what to write here. What we want to say is that P1 and P2 are mutex if all ways that P1 can be produced and all ways is mutex with all ways that P2 can be produced, and by this mean any action which produces P1 is mutex with every other action which produces P2 essentially. If there is no actions A1 and A2 in the preceding layer such that P1 belongs to effects A, P2 belongs to of A2 and or in other words, if we can find two actions A1 and A2 which are not mutex and A1 is producing P1 and A2 is producing P2, then we can say P1 and P2 are not mutex essentially. But if you cannot find, so if there are no actions A1 and A2 which satisfy this condition, then we say that they are mutex essentially. So, let us sort of try to construct this example from here. So, the first thing you will observe is that in this layer A2, so A2 is a superset of A1. Everything which is there in A1 will always be there in A2. Why? Because we have this no op operations which are carrying forward everything which was here, which made these all these actions possible, they are being carried forward here, and therefore, they will be possible. So, apart from this pickup B, unstack C from A and so on. So, for example, it is always possible for me to say that my first action is to do nothing, okay, for some strange reason, that I will do a no op. If I do a no op, then I can always do a pickup B after that essentially, or I can always do a unstack C A after that, which means these two actions must come in my layer. So, everything which is there in A1 plus something new. What are the new things we can have? So, we can see. So, I am not going to write all this again here, ideally you should copy it here, but it is a bit of a work. So, I will just write this as A1 plus the following, that you are holding B, you can do something with B, right. You can stack B onto C. Why? Because all the conditions are there. If you have picked up B, then you are holding B, and then C is clear because no op will make it clear, and that is about what you need, right. So, you can stack B onto C, or you can stack B onto, no, you can put down B. These are two extra actions that I will add to my listing. Likewise, for this one holding C, I will add stack C onto A, stack C onto B, put down C. So, I have this same A1 set of actions, and remember all these no ops are always there for every predicate in my action proposition layer, every proposition in my proposition layer there is a no op action which takes it forward to the next layer. That is always part of the graph, plus anything new that I can add essentially. The only condition I need for adding a action is that its preconditions must be available in a non mutex fashion essentially. So, again to repeat, if you want to stack B onto C, what do I need? I need holding B, of course, I need clear C, and that is about it essentially. And of course, it will have its effects, it will say arm empty, not clear C, and not holding B, and so on essentially. So, in this process I construct the planning graph layer by layer. At every layer I have to find what are the mutex relations and put them in, and as you can observe the planning graph is growing monotonically essentially. It starts with these propositions, then it expands and then it expands, because whenever a proposition gets into the planning graph, then a no op will take it to the next layer, only new ones may be added. So, for example, when you stack B on C, one thing that gets added is on BC, plus of course all these P propositions. So, it is growing monotonically. It also can be shown that it is growing as a polynomial of the original problem size, and in general the size of the planning graph grows increases polynomially essentially. So, that is the first phase of GraphPlan, you construct the planning graph. So, till what stage? So, stage 1, there are two possibilities, that either you have reached a stage in which a plan may exist. So, let us say we have a 2-armed robot for argument's sake. So, we can pick up C in and pick up B, unstack C and pick up B in as action 1. Then at the second layer we can put down C, and also no okay. So, let us say in the first layer you unstack C and in the second layer you put down C and pick up A at the same time. Then in the third layer you pick up B, and in the fourth layer you stack B onto C, and fifth layer you stack A onto B. So, you can get a 5-step solution if you had a 2-armed robot. We know that for a 1-armed robot, as we saw in the last class, there is a 6-step solution. So, the stage when ends if 1 all goal predicates or propositions exist in a layer non-mutex. If you can find all the goal propositions, what are the goal propositions we are interested in? On B, on AB and on BC. If they happen to be in a proposition layer and they are non-mutex, then we stop this forward planning graph construction exercise and we go to a backward search. So, typically you could do something like depth first here. Remember that the problem is still intrinsically hard, but you could use other methods. So, for example, people have tried constraint satisfaction methods and so on. What are we looking for? We are looking for, so at some stage, so let me write those things here on BA and let me write them here on BA and on AB and on BC I am looking for these propositions. So, if they occur in some layer and they are not some, let us say P n, and they are not mutex, then I start a backward search phase and say, can I find all the sub goals of this in the previous layer in a non mutex fashion. Okay. Now, obviously, these have positive links coming from actions, and those positive links could be in the final solution that we are going to construct. What are these positive links going to be? What are those two actions which will produce this? Stack and yeah, but are they non mutex? I am looking for non mutex actions. So, I need to do this backward search looking for non mutex actions with non mutex preconditions. So, as you can guess, this is a no op action essentially. So, in my previous layer, if I have stack, and I am saying that because I know what the solution is, the last action must be stack A1B, and but essentially what the algorithm will need to do is to search. So, from this goal set, find an action set which assumes this goal set which is non mutex. So, stack A and B and stack B on C will be mutex, because both of them. So, stack A and B makes B or makes B not clear, and this needs or something like that. So, something will come and they will be mutex essentially. I need a goal set here and then an action set here, then a goal set somewhere here, sub goals, and then actions, and then sub goals, and then actions, till I come to the initial layer, and nowhere do I encounter a mutex relation. If that is the case, then I have found a plan. As you can imagine, this will be found only in the 6th layer for this particular problem, because we know by now that it needs 6 actions. But in the 6th layer, we will find this stack A B mutex with nothing, and its conditions will be mutex, will be not mutex, and one of them will be holding A and clear B, and on B C already will be here, and so essentially you will be able to find a path back. So, this backward phase is a search phase, which will try to solve every goal set with sub goal set with another sub goal set right up to the start state in a non mutex fashion. So, to do this, of course, it will have to do some trial and error. It will try this sub goal set, another sub goal set, could be just 2 actions, for example. You can see that it may try, but of course, it will not find a solution, because for 2 no op actions to happen in parallel, it must need 7 steps. As we know, we need these 6 steps anyway, but it could try this, it could try this combination, or it could try this combination, or it could try some third combination, and it will do some kind of a search. And typically, the original GraphPlan algorithm written by Blum and First, the backward phase was depth first search essentially. Okay, so, in the forward phase, you go, all goal propositions exist in the layer non mutex, you do backward search. If it fails, then you extend the graph by one more layer and do the same thing again. Now, notice that when you extend the graph by one more layer, you will still get those things non mutex essentially. So, you need to convince yourself about this, that once a goal set is non mutex, it will remain non mutex in the next layer also. But it is possible that some sub goals may not be mutex, some sub goals may be mutex, which is why you need to extend the plan further and further essentially. So, there are 2 cases. One is that a plan exists, in which case stage 1 ends when all goal propositions are found, then the backwards phase begins. Else, so I will just write else, meaning you have not found a plan, extend planning graph, and you keep doing this. Extend the planning graph, search for a plan, extend the planning graph, search for a plan, and you can imagine that because we are doing this iterative deepening, if it finds a plan, it will be the shortest possible plan essentially. The other situation is no plan exists. Now, this is a little bit tricky essentially. So, I do not think we will have the time to go into details to thresh out the conditions when the algorithm should say that no plan exists. But the general idea is as follows. So, what is happening in this planning graph extension stage, that more and more propositions are being added. So, more and more things will come into play as non mutex. So, initially for example, you might say pickup B is possible, unstack C from A is possible, and then because we already have clear C somewhere, we can say after pickup B you can stack B onto C, and because we have unstack C from A, we can pick up A in the next section and so on. So, it might be that you might see the propositions appear in the proposition layer, but they may not be mutex. At some point they will be mutex, and then you will search for in a backward phase, and you will find that at some layer, some preceding layer, they become mutex, and then you cannot complete the backward space search all the way to the start state. So, you find that they are mutex, so you abandon it. You have tried all possible combinations, and at some layer n they are mutex. Then we extend the planning graph to, let us say it was at layer T, and then we extend it to layer T plus 1, and then we come back and search essentially. So, what Blumen first showed was this condition: if the sub goal set that you are trying to solve remains constant, sub goal set at layer n remains constant when you extend from planning. What is a sub goal set? The sub goal set is a set of sub goals, where each sub goal is a set that you want. So, for example, for on AB, on BC, we will have the sub goals as you want to do stack A on B, holding A, clear B, and on BC. These three actions would be in the sub goal set. This action will have different actions as a sub goal set. Some other action will have different actions as a sub goal set. So, we have a set of sub goals, set of sub goal sets. If the set of sub goal sets does not change as you go from layer T to layer T plus 1, as you extend the planning graph from layer T to layer T plus 1, then you can terminate by saying there is no plan essentially. Okay. Or to get some intuitive feeling behind this, what happens is that as we construct the planning graph, first the set of propositions stabilize, that no more propositions are added to the set. We have added everything possible essentially, and then the set of mutex relations stabilize, which means there is no more mutex relations are added. But even then you have to be a bit careful that you can extend it by one more layer, and you might still find a plan essentially. And what Blumen first showed was there is a slightly complex condition, which says that if you extend the planning graph from layer T to T plus 1, and the sub goal set at some intermediate layer n remains constant, then you can be sure that you will never, because if you are not being able to add a new sub goal set when you move from T to T plus 1, you can never add any more, because the set of propositions has stabilized, the set of mutexes have stabilized. So, there is nothing more you can do after that essentially. It takes a bit of a time to figure this out essentially. Okay. So, to summarize, the GraphPlan algorithm works in two stages. In the forward stage, it constructs a planning graph which contains these 4 kinds of edges: the precondition edges, the positive effects, negative effects, and mutex relations. Once it finds all the goal properties which exist in a non mutex form in a layer, it goes to the backward phase, tries to search for a non mutex substructure in the planning graph where there are no mutex relations, which means that those actions are possible even if they are in parallel. If it cannot find, it goes back and extends the planning graph by one more layer, again goes into the backward phase and keeps doing that till at some point either it finds a solution, or this criteria which we described somewhat briefly is met, where it says that no plan can be found essentially. So, the planning graph gives us an optimal plan in terms of the most the shortest time span or the shortest number of steps in which a parallel solution can be found, if there is a parallel solution. Of course, keep in mind that the blocks world domain that we are talking about has no parallel solutions, because it has a single arm robot, but many domains may have parallel solutions, and what GraphPlan does give us is the shortest time in which a parallel solution can be found, and we can of course always linearize that by putting all the actions in any layer can be linearized in any order essentially. What it gives us is a set of actions at layer 1, set of actions in layer 2, set of actions in layer 3, which is the parallel shortest possible plan essentially. So, it is an optimal algorithm, in a sense it gives you the shortest plan, and it can solve much larger problems than the earlier algorithms could essentially. So, I think I will stop here with planning. We do not have time to go into the other algorithms. What we will do in the next couple of lectures is get a flavor of constraint satisfaction problems, which is actually a very big area in computer science in AI, that there are people who try to pose everything as a CSP, and there is a huge amount of activity writing solvers for constraint satisfaction problems. So, what we will do is we will just get a flavor of how to pose a problem as a constraint satisfaction problem, what is the constraint satisfaction problem, and what are the basic idea of what are the algorithms that we use for solving it. The interesting thing about studying CSP, constraint satisfaction problems, is that it gives us a opportunity to combine search with reasoning essentially. That you can do some amount of search, but you can constrain the search by doing some amount of reasoning, and constraint satisfaction problems give us a natural way of doing that essentially. We will try to get a flavor of that in the next few lectures, and then we will move on to representation proper with first order logic essentially. And okay, we will stop here.